Yay, thank you very much for the kind introduction and also for the invitation. So I'm really excited to teach this a workshop today. As Lloyd already mentioned, I have a bit of a background. Maybe let's start with that slide and then go back to the first. So that's a bit of my background. I mainly work on adaptive structures and flight systems. So these are a couple of examples here of robotic systems that I developed with collaborators. So for example, on the top, that was a flapping wing robot that we developed with collaborators at MIT during my postdoc. And then the bottom part, which is my main work on these adaptive wings. So basically wings that can change their shape inspired by birds to operate optimally over different operating conditions. So these are two types of like fixed wing drones that we basically changed the main wing structure with these morphing wings, and the goal is to improve the performance for drones, but my interest is mainly basically on wind energy, so applying these type of systems on wind energy. And one of the big challenges, of course, modeling these multi-physics systems. So that's where my interest started in SINDy and data-driven modeling. So in a sense, we have the governing equations of the fluids and the structure, but to solve them quickly enough to run a controller, for example, on these systems is challenging. So my main idea is to use SINDy for model discovery for control of these type of systems. And so all these slides are on my GitHub. I think Lloyd shared the link with you. So if you're interested in the work and in what SINDy can do and the latest extensions, you find the links here. Now, in today's workshop, we're going to talk about SINDy. So back to the first slide. With videos, usually it crashes. Now, there we go. Now, so the idea is, the goal is the same like yesterday, I think, with Miles's talk. We have a bunch of data, and the idea is to learn a model that is not just useful for forecasting, but it can also tell us something about the data that we collected. So basically learning an interpretable dynamical system model purely from data. Now, how SINDy works is basically that we start from a data set. We take a couple of assumptions. For example, if we have a time series data set, we want to learn an ordinary differential equation. And what SINDy does is it doesn't just fit parameter to a given model structure, but it can also identify the model structure itself. So for example, in this case here, the famous butterfly attractor or Lorentz system, we assume that it has three states. We measure the three states, and then we learn this ODE that has linear terms in the X state, quadratic terms here, and also quadratic in Z. Okay, so that's the whole goal of SINDy, to both learn a model structure, in this case an ODE, and also the coefficients of this ODE. So very similar to, I guess, what Miles was teaching yesterday with the symbolic regression. But here, instead of using genetic algorithms, we are using a slightly, I would say, simpler approach. But let's decide on that later. Okay? So I structured this workshop I have a bunch of slides, but throughout the slides, I'll always show a couple of tutorials. I usually teach this workshop in MATLAB, but I converted everything into Python, so don't judge me on the Python code, but it works. And you can find it all also on my GitHub. If you prefer working in MATLAB, you can just click on either the Filton or the Amsterdam workshop. So they should contain the exact same tutorials also in MATLAB if you're more familiar in MATLAB. Okay? Are there any questions to start? Any curiosity before we jump in? Why are you here? What types of models do you want to learn? I heard that we have quite a lot of biologists in the room. Some people from chemistry. No? Engineers? Okay, so good mix of people. Very nice. All right. So let's start. Oh yeah, that's also a bit of an advertisement slide first, maybe in terms of the success story so far with SINDy. So I think I prepared this slide for for the Cambridge workshop where I met Lloyd, and this was a workshop in fluids. So SINDy has lots of applications in fluids so far. So for example, one of the first examples that Steve Brunton already published in his first paper was learning the time history of these POD coefficients of the vortex shedding flow. Really cool example in airfoil shock waves, high Reynolds number cases. One really cool application of SINDy is also this one here. So you can't just learn ordinary differential equations, but in that paper they extended it to SD, stochastic differential equations, plasma dynamics. So this is a really cool a group or a set of papers by Alan Kaptanoglu, who is now faculty at NYU on plasma dynamics, real-world data sets, so experimental data sets in fluids, and then also higher Reynolds number turbulence relearning problems. So again, all the links to the papers, kind of like a really nice set of papers with cool applications in terms of, you know, getting some inspiration with how SINDy can be applied. Okay, now, yeah, so this is the outline exactly. So in the first part, I'll introduce vanilla SINDy, so the sparse identification of nonlinear dynamics. So how can we learn these nonlinear dynamics, these differential equations from data first, a general intro on it, and then I will directly jump into a Python example on how we can learn the Lorentz system ODs, not using PySINDy. And then I will show how we can solve this tutorial in 2 lines of code with PySINDy. So that's a package that was developed by the guys in Seattle, which is really nice, contains all the baseline SINDy methods and also the extensions and a really cool set of tutorials. So I also have a bunch of links in the slides here to directly guide you to the PySINDy tutorials, but I mean, you can also just check it out yourself. So I think they have 15 tutorials there that are really useful. And then I will conclude the first part with a small tutorial on the challenges and limitations. So when does vanilla SINDy break? And that, of course, then motivates the extensions. And in the second part of the tutorial, or part 2, 3, and 4, I will talk about the library. So in a minute, I will tell you what the library of the SINDy problem actually is. And then we'll talk about model selection, basically hyperparameter tuning. We'll also see that there is one hyperparameter that is super important that we need to choose somehow. There's a bunch of different methods to do that in a more systematic way. And then the last part of the tutorial will be on noise robustness. So depending on the sensors that you choose, so for example, in engineering, in the morphing wing case, very often we have some sort of strain sensors or inertia measurement units on the drones, and the data that we collect is usually terribly noisy. So how can we still learn accurate models if we have noisy data? These are 2 cool extensions, the weak form and the ensemble SINDy. Yeah, so that's it. I haven't really practiced this workshop in a 3-hour setting, so let's see how far we get in the first hour. But I want to mainly focus on the tutorials, and I want you to run a code. So if you already have your laptops up, just go to my GitHub, get the tutorials running. I also have this binder notebook incorporated in the tutorials. So if you have never run Python, just click on that, and an additional tab should open up in your browser, and you can run that on a server without having to download anything. Okay? Good. Now, yes, let's start with SINDy. So I already mentioned that on the title slide. So the idea is that we start with collecting a bunch of data. We take some assumptions. So for example, we want to learn an ODE, or in case if you have spatial temporal data sets, like here, basically a time series of snapshots of the flow around this cylinder. So the flow basically enters here, and then this black dot here is a cylinder, and then the flow around the cylinder basically starts shedding this vortex, and we have a time series of that. So in case we have these type of data sets, we could also learn a partial differential equation. So that's basically the assumption, what type of differential equation do we want to learn. And then SINDy helps us, as I already said, to learn the model structure and also the coefficients. So not just the fact that we can learn, for example, sigma, rho, and beta of the Lorentz system equation, but we can also learn that this is a quadratic differential equation. Okay? That's basically the idea. Identifying ODs and PDs directly from data. Now, how does it work? So as I said, we start with collecting data. So this first tutorial, or this first introduction, is a so-called relearning problem. So we basically use the differential equation to generate data, and we apply SINDy to relearn the system of equations that we use to generate the data. So the data set itself comes from this quadratic ODE with 3 states, so states x, y, and z. And we start with, for these coefficients, to collect this time series data. And this is basically how the data looks. So the state x, y, and z over time. And if we look at the phase space, this is the famous Lorentz attractor. So that's basically where we start. If you're a biologist, you might have some video data of slime mold growing. If you're an engineer, you might have, as I said, some strain measurements of a deformable wing structure over time, you name it. Okay? Then in the first step, okay, we collect this data. And the second step is to compute the time derivatives. Okay, so this is super important. And very often we just assume that this is straightforward, but very often it's not the case. So computing time derivatives can be fairly challenging in case we have noisy data. And just for the sake of completeness, I also added a couple of different types of methods to compute time derivatives. I think most engineers might be very familiar with those methods, of course, starting with the most straightforward and simple method, finite difference, and then basically methods that can also deal with noise. So for example, if we first smooth our data and then take the finite difference, or a really cool method that is also implemented in PySINDy is if we smooth the data with a polynomial, we can then directly take the analytic derivative of this polynomial to compute the time derivatives. So just 3 examples of how we can approximate time derivatives. And in my first tutorial, I also show how to use, for example, a 4th order central difference method directly from, in the case, not noisy data, because we'll see once we crank up the noise in the relearning example, we won't be able to actually learn the differential equation. Okay, so if someone hasn't seen this, again, slide is on GitHub. Quickly, I think I even added, oh no, I didn't. But yeah, you can just check out the different 3 methods. And there's also a bit of an explanation in the PySINDy tutorials on the PySINDy GitHub itself. Okay, so important second step. First, we collect the data. Then we compute the time derivatives. And then we built a library of nonlinear terms that we believe could describe the data that we collected. So in the case of this data set, we could assume, oh, probably we have some polynomials up to order 5 that could describe this data. Now, this is, of course, quite arbitrary, you might say. It's like, okay, the whole point is learning the ODE. But yeah, usually we have a bit of an understanding. So in fluids, for example, most of fluids are governed by the Navier-Stokes equation. So we could assume that there might be some quadratic terms in the dynamics that we want to learn. In biology, I believe you have lots of rational functions that describe how biological processes work. So you might want to learn rational functions in that case. So here we build, given our understanding of the field and the data, a library that we believe could describe the dynamics. Okay? Is that clear? That is super important. So 3 steps: collecting data, time derivatives, and then building a library of nonlinear terms. So this is basically our data, this 3-column. And then if we want to build this library, we would just at each time step take, for example, the x step and square it. And that would be this new column of data. So this is the data library. Any questions in terms of the library? Very good. Oh, yes. Absolutely. Yeah, really good point. So if we have three states, if we have polynomials up to the order 5, we have a library of the size 100, I don't know. Whereas if we have, for example, spatial temporal data like the vortex shedding, which can be thousands and thousands of states, this would completely blow up and we couldn't actually build this library. So this is a really good point, and lots of extensions and lots of research is currently basically developing methods where we first try to find a coordinate transformation into finding states which are basically sparse and can still describe the rich dynamics of whatever we're looking at. So for example, with the flow examples, we often do POD first, and then we learn a differential equation on the evolution of these POD modes, okay? But yeah, so very good question. There are certain limitations with the method, which is if you have high dimensional states, you first need to think about that. Any other questions? Exactly. So with the vanilla SINDy, we want to learn a linear combination of these terms. And that's a very good question, because that basically limits the types of functions we can learn. So I mentioned rational functions, but if you don't add your 1 over 2 plus x squared in the library, you won't be able to find it. So how are you going to do that? And that's also a couple of extensions to help us how to deal with those type of functions. Mm-hmm. Well, yeah. So that's a very good question, because with the Taylor expansion, you can usually approximate most functions very well, and that's also kind of like the answer why these polynomial libraries work very well. Now, if you want to better understand the dynamics, the data set that you have collected, you might want to add different types of functions for the sake of interpretability. And one other benefit or idea that I will introduce in a second is also we want to learn models that are sparse and not overfit to the data. So if we add different types of function to our library, the models might be sparser. And that's exactly one example that I will show on a pendulum data set, where if we add a sine term, the model will be extremely sparse. It will have 2 terms. Whereas if we just have the polynomial library, we basically learn the Taylor expansion, which is not sparse, still accurate. So it does the job in terms of forecasting. But the benefit of SINDy, and I think also in general of symbolic regression, is to find a sparse, so a small model that best describes the dynamic for the sake of interpretation of whatever data we have. So, but it's a very good question. Yeah. Any other questions?
Don't worry, it's just the normal Tuesday morning text.
That is good. We will wait for the next question.
Do people combine this with, let's say, genetic algorithms? Because I guess you could do this and simultaneously do the kind of like optimization if you want to go beyond this structure.
Well, you could wrap around the genetic algorithm to kind of like tailor your library and then have, I mean, I haven't gotten to the optimization yet.
Okay.
So this is a good question also, but let me maybe continue with the next click where I discuss what we're actually solving, because so far I only talked about collecting data and building this, but I haven't really introduced what and how we are actually going to solve it, because your question is very good, and people think about how to build this library with an optimization around it, but I first want to introduce the optimization within the SINDy algorithm.
Yeah. Well, I mean, it kind of looks like a sparse linear solver.
That's exactly what we're going to do, yes. Okay, so yes, last question, and then I want to introduce the optimization. Mm-hmm. Not necessarily, because you just, no, not necessarily. No. What, yeah. No, that is not a constraint imposed on the library terms, I think. No. You need to be able to compute the library rows given your data, but that is possible with all functions. So again, not necessarily, because you collect your data, you compute the time derivatives in whatever way. The library terms, do you have a particular function in mind? Okay, no, I think there are no constraints in terms of this choice of the library function. Okay, good, hey. Yes, now what are we going to do with that? We collected some data, we built this library of nonlinear terms, we computed the time derivatives with finite difference or whatever approximation methods of these time derivatives, and then we solve a sparse regression. So the idea is basically for all the three states in this case, so x dot, y dot, and z dot, we solve this optimization problem. And the optimization problem basically contains two parts. So we have a least squares fit of our x dot, so of the time derivatives, and the library of nonlinear terms. And we have this regularization term here. So basically what it tells us is that we want to find the best fit linear model that can describe the time derivatives while it should also be sparse. Okay, so we have a least squares fit. We all learned that in high school. And the regularization that should remove as many terms as possible such that the differential equation that we learn is interpretable and also generalizable, so that it basically doesn't overfit to the data. Okay, and how we solve this, it's a bit misleading here. So in the first SINDy paper, there was an L1 penalty. Then it's somewhat transformed into an L0 penalty, but under the hood, what is actually solved is a sequentially thresholded least squares, so a hard thresholding algorithm. And what that means is basically this here. So the whole SINDy optimization is just 10 lines of code. And you'll also see it in the Python script. So we start with an initial least squares. So we want to find the best fit of this data. So basically in MATLAB, that's a simple backslash. But what this operation does here is an initial least square. So we want to find the coefficients of the ODE that best fit our data. And then we run this loop where we start removing terms in C that are smaller than a threshold. And then we rerun our least squares problem here on the smaller library. So iteratively, we start removing terms from the library to learn a sparse differential equation. That's basically the SINDy optimization. Hard thresholding on least squares. So we solve least squares, we look at the coefficients that we learn. Coefficients that are smaller than a threshold, we say, they're probably not that important, we set them to 0. Okay? So that's basically it. So this is not, we're not solving an L0 regularized least squares, but we solve an approximation of that using this hard thresholding. Okay? Yes, it's a very good question. So they're either 0 or a particular number. Okay, first that. And then second, I think the question goes a bit in the direction, okay, how do you choose this lambda That's, I think, the main question. And there will be a whole couple of slides and 3 methods in terms of selecting those. What you can always do is, because in most cases, the most expensive part of this framework is collecting the data. So there are a couple of applications where collecting data is cheap, but in most cases, collecting data is expensive. So you can basically, what I'm saying, run this algorithm 100 times over different thresholds and basically get a good understanding of how the model structure changes. And I also have one of the tutorials where we can kind of like play around with a little slider in terms of how the model that we learn changes with changes in that threshold. But that is basically the main hyperparameter that either as field experts or with the methods that I will introduce in an hour can choose. Okay? Any other questions in terms of that? So you'll see that in the tutorial, but that's super important to understand. So SINDy, under the hood, collects some data, builds a library of nonlinear terms, we compute the time derivatives, and then we solve this sparse regression. Okay? Now, to go back to your answer, we could now wrap a genetic algorithm around this and start playing with different libraries, for example. So some sort of a combination between Miles's work and the SINDy algorithm. That would be possible. The benefit here is that we don't need to solve an expensive optimization. So solving this here takes less than no time. So, which means that we could incorporate it into a more expensive optimization. I don't have a paper in mind that I could share that discusses this, but why not? Any other questions? Yes?
So in the case where like you have like something in your library that starts off smaller but eventually like dominates the function, there would be a chance that this could like eliminate that early and then not pick up on it, and so not get the overall relationship? Is that like a thing that could happen, or would it or like, I guess it would depend on the data you put in, right?
Yeah, possible. I think one discussion and one challenge is a bit, I think that also goes in the direction of, okay, what if some coefficients are very small and you threshold them out, but they're important? So there's also a couple of works around that in terms of normalizing the library terms, in terms of multiscale dynamics. So if you have a problem in mind in your field, no, okay, but it can be an issue that that terms that are relevant are thresholded out because this is not the most elaborate optimization strategy, okay? All right, so this is sparsify dynamics. You get a dynamical system that is a sparse, the SINDy optimization algorithm. And what we then get out here, shown in MATLAB notation, or yeah, this MATLAB array, is a sparse matrix of coefficients that best describe these dynamics. Okay, so this is basically the result that the optimization will spit out. So we see that our sigma is probably 10, so minus 10 plus 10. We have 28 for our, which one is that again? Rho, I believe. And our beta, our z, is minus 8 over something, 2.66. Okay? So this is basically what we learned. And we also learned that we have in x dot a linear equation, so only x and y are active. We see that in the y direction, we have xy and x times z, so the first quadratic term that is active. And in our z dot direction, we see that we have z and x, y active. Okay? So with SINDy, we learned the structure of the ODE and also the coefficients. All right. So yeah, I think let's just jump directly into the tutorial. So everyone that has a laptop should just open the GitHub, and then we can start. With that. All right. So we start with the first tutorial where we just go through the steps of learning the Lorentz system ODE. The ones that never use Python, just directly in GitHub, go on the first tutorial and click on this binder button here, and it should open an environment where you can directly run the code, okay? Or if you want to run it in MATLAB, just go to the Filton workshop. Okay, so a couple of packages that we need to import, unimportant. I have a plotting file that we use that we grab from the utils.py file here, but then we set the random seed for reproducibility. Here we don't actually add noise, so it's a bit unnecessary. A couple of settings for the integrators. Now, as I said, this is a relearning problem. So we start with a known ODE and generate data. Generating data basically means that we numerically integrate this ODE. Therefore, we choose Runge-Kutta 45 solver. You can also choose different types of solvers, some tolerances here, okay? And then we start with generating the noisy, or generating the data, okay? So these are the parameters of our ODE. This is the initial condition. You can also play around with that, the time step, and we will generate 10 seconds of data. So from 0 to 10 is our time span. And here is where we define the Lorentz system ODE. So x dot is equal parameter 1 times x2 minus x1, etc. So that's our Lorentz system right-hand side. And then we can generate the data by solving this initial value problem. So our initial condition x0 defined up here again, and then we solve this system of ODEs, okay? And then we can add a bit of noise if we want to make it more challenging, but in this first tutorial we add no noise here. And then we can plot the time series. This is basically what we get, okay? Any questions in terms of that? Just generating some data, okay? Good. Then second, we compute the time derivatives. Now here, I just wrote out how we can use, for example, central finite finite difference, or central difference, basically. So the time derivative of our states are defined here, and I think most engineers that should be standard bread and butter. If you have a question in terms of that, basically we just compute the gradient, the time derivative of our data. We approximate it with this central difference. So we take the data point ahead of us, the data point behind, and then we place a line through it. And we look at the change of our state. So we divide it by dt. And depending on the order of our finite difference, this looks slightly different. But that's basically the idea. I think I just butchered the explanation of finite difference, but I think you get it, and it's on camera. That's great. Anyway, you have the slides, and we can play around with it a bit later and see in one of the tutorials, actually in this one here already, how the order of the finite difference scheme can affect the fit of our model. Okay. Then step number 3, we build our library. Okay. So we define this function pool a data here, where we basically take our data x, y, z, and we build a library of polynomials. Okay. So here we define the order of the polynomial, and this is just a simple script here where we can define polynomials up to order 3. So basically we just take our data, and polyorder 1 is just the states, polyorder 2 is the states squared here, and then we basically stack these columns next to each other, and we build this library. Okay, so this is a data library in the end. Okay, and then we call this, and then shall we quickly print the library? That's maybe also, I just prepared printing the size of the library. So it has 969 rows, so that's the number of time steps, and 20 columns for a library of up to cubic terms. Now, that's the library. Let me just do this. There you go. There we see. This is basically just a large data array that consists of the different states and different polynomials of up to third order, and then number of rows is the number of time steps. Yes, please?
What do the numbers represent? So the position of the library is like, does each column...
It's a very good question.
X, Y,
Exactly,
Z?
exactly.
Okay.
So this is our constant term, 1, x, y, z, x square, x, y, x. I don't know actually, but that is, we can actually have a look here. The implementation here is, yeah, it's I think x squared and then x, y, x, z, and then y, z, etc. So building the library. Okay. So each column is representing one nonlinear term. And then we compute our sparse regression, and that's exactly the 10 lines of code that I showed in MATLAB notation in my slides. So we start with, okay, no, that's just the definition. Let's first look at these here. That's basically how we call it. So we define a threshold, that is our lambda in the slides. We have the number of variables or states, so that's 3 here. And then we call sparsify dynamics, which takes as an input the library matrix, the left-hand side. So these are the time derivatives, the threshold, the lambda, so where we want to basically chop off the coefficients that are smaller than that threshold, the number of states. And then we go up here into the function, and we see that we first solve linear least squares to get our first guess of the coefficients c. And then we loop through this loop here, and we remove, and that's important here, so small coefficients are defined as being smaller than a certain threshold. And we set the small coefficients in our C, in our array of coefficients, to be 0. Okay? And then we solve our new least squares problem on the smaller library. Okay? That's basically how we do it. Now, why are we doing this 10 times? Why don't we define, for example, a convergence criteria just for the sake of keeping the code as short as possible? So you can do much smarter things than that. One explanation is also, well, it doesn't really take that much time. So for the sake of this teaching tutorial, 10 times is enough. Steve Brunton chose 10 when he published his work, and it worked. So all not the best explanations. And I already see the optimization heart burning here in the first row. So there's better ways of doing this. Yes?
Could you, like, in a small problem generate all these different subsets?
Absolutely. Yeah. So we always say that, that is not possible, but Lloyd has a fantastic extension of SINDy, the Bayesian SINDy, where under the hood, that is what he's doing, because you can afford it. You don't have too many problems that you would need to compare with. So you can solve the L0 regularized least squares in also no time. How much does it take? 0 time? It's much less time than annoying. So you can play around with Lloyd's code, and it's on my laptop. It runs in no time. So that is very true. Okay. So this is sequentially thresholded least squares, and this is exactly what I showed on the output on the slide. So this is the identified SINDy model, identified ordinary differential equations. The ordinary differential equation, x dot equals minus, what is it? Minus x plus y da da da, y dot, and z dot. Okay? So again, the structure and the coefficients of the differential equation that we want to learn. Any questions in terms of this step number 4? That kind of concludes the workshop, and we can now all go home. No. There's a bit more to that, we see, but that is really the main, the key takeaway is that, oh, okay, you have a bit of data, you want to learn a differential equation, it's actually not that hard, right? And it's a really cool method, but there's not too many moving parts in it. Yes, please. Sorry? Yes, so that's the model selection part in the second part of the lecture. How I'll have the challenges tutorial where we can just play around with it. Again, since the method is fairly quick and usually data collection is time consuming and expensive, you just run a sweep over lambda from small to large. If your lambda is 0, you basically recover the least square solution. So you won't have this sparse differential equation, but you will have a dense solution. So the whole array here would be populated. If you have a very high threshold, you will recover the trivial solution x dot equals to 0. And the truth probably lies somewhere in between if it's within your library. So that is.
If you wanted to do this for second order differential equations, could you just take the derivative and put that in the library? And
You
have
could.
the second derivative on the left?
Yeah, absolutely. So yeah. If you have a second order ODE in engineering, that's usually what you have. Once you have inertial forces, that's what you need to consider. So you would have your second derivative on the left-hand side. You'd still have your library, and we can basically solve that.
But
Yeah.
inside the library, you put
Yeah.
in the first
Yep.
derivative.
Exactly. Yeah. So with the PD example, we'll see that you can add spatial derivatives to your library. You can add whatever you want, basically, depending on the type of differential equation that you want to learn, whether that's a second order ODE, whether that's a PDE. So we'll see that this approach is quite flexible in terms of taking whatever data in. Okay? And I think in the afternoon, we'll discuss this a bit in the tutorial where we don't have this standard approach of the left-hand side is the first time derivative. And in our library, we just have polynomials, but we need to be a bit smarter about what goes left and what goes right. Good. All right. Now, yeah, important next step is that, okay, evaluate the performance of the SINDy model is maybe a bit misleading because I also think, what we just did, looking at this array here, is very much evaluating the SINDy model. Because what we want is to learn something about the data. So the main evaluation for me is always, okay, what type of differential equation do we actually learn? But anyway, once we have the differential equation, we can also solve it, okay? And this is here in step 5, evaluate the performance of SINDy model for forecasting. Oh, I actually mentioned it. So here we define this helper function to solve the SINDy ODE if the ODE is written down in this type of array structure. So we choose a new test trajectory, so a new initial condition. We solve our initial value problem here first again with the true Lorentz systems to basically have the test data set. And then we can also numerically integrate our learned SINDy model, okay? Then we can plot the comparison. And this is basically the comparison here, okay? So the colored line is our data, test data starting from a new initial condition. And the black dashed line here is how well our SINDy model can forecast this chaotic dynamical system, okay? So actually for a couple of lobe switches of the Lorentz system, we can track the dynamics very well. And then of course at one point, because the dynamics are chaotic, they diverge. That is okay, but pretty nice result to start with. And we can also see here if we plot the attractor that yes, for quite a while we have a perfect match, and then we, I guess, get one lobe switch wrong here, but the structure of the dynamics is the same. And the reason why we diverge is because we have this small offset here. Okay. That's basically it. Okay, so we can evaluate the performance. Now, with the guys in, is this the next step? Da, 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 da. I think half of the tutorial is missing. Do you see the PySINDy part in your tutorial?
Yeah, number 6.
There we go. Wow. Okay. Now, the guys in Seattle, they developed this Python package, PySINDy. So everything that we just did can also be done with 2 lines of code, which is very convenient. So basically, we can install our PySINDy package, define a SINDy model here by this step here, and then we can fit a model given our data x, and this is the model that PySINDy would find. And then we can also evaluate this model directly here with model.simulate with our new whatever test initial condition and compare it here in this plot with the true dynamics. Okay? And this is the comparison between the PySINDy model and the data. And what is interesting here is that, well, for some odd reason, both trajectories, they diverge a bit earlier. And the reason for that is that the default setting in PySINDy for computing or approximating the time derivative is a second order finite difference. So that's a nice example of how the order of your time derivative approximation can affect the dynamics that you learn. If you look at it, we had 9.999 above with a 4-4 finite difference, and here we get a less accurate OD. Okay? So what we can do to solve this problem, if we consider this a problem, is to define the different parts of our PySINDy model. So we can choose the select sequentially thresholded least squares optimizer. We can choose the differentiation method, finite difference, order 4 now. And we can also choose the polynomial library degree 3, which is, I believe, anyway, the default. So the only thing that we actually do here is change the order of the finite difference method. We solve the same problem again with PySINDy here, and then we get the very accurate model and the exact same results. Remember, we only had the wrong lobe switch towards the end of the trajectory. Okay? Now, first, are there any questions in terms of the PySINDy implementation? Yes?
I guess when we introduce noise,
Yep.
when we introduce noise to the data, like how well does it work and how can we deal with that?
Yeah, very good, very good. So if we use finite difference second order, it won't work very well. So we will see that in the challenges tutorial, and there's many ways to deal with noise. That was kind of like the first set of papers that followed up the first SINDy paper in terms of, okay, how can we deal with noise? There was a couple of like different directions, first like extensions to PDEs, other types of libraries, but that is one of the main questions, because in reality, we usually can't afford the most expensive sensors. So noise is a reality, and there's different ways to deal with that. Okay? So I will have the answer in 1 second. Okay? Any other questions? What we could do is We have another 30 minutes in this first part, no? So I will also introduce the challenges tutorial. I think I have one slide. And then we can spend the last 15 minutes, the first part, just tinker around different tutorials, and then move on to the second part where we discuss libraries, model selection, and noise-robust extensions of SINDy. Okay? That makes sense? Lloyd is nodding. Good. All right. Yes, challenges and limitations, exactly. So that's the next slide in here. So how much data and what quality is needed? That's you know, one of the questions, and often then poses a challenge. How do we actually choose the library? One of the first questions this morning. If the dynamics that we want to learn are not included in the library, it will be quite difficult to learn it. What optimization strategies are there? Are there different types of regularization that could help with it? We'll see that with the PDE example, where we introduce additional types of regularization to help solving the problem. And then model selection, also a question that was already asked. How do we tune that lambda hyperparameter? And in brackets, because I won't discuss it, but that was also one of the first questions. If we have a high-dimensional state, how are we dealing with that? Because if we want to learn a PD, high-dimensional states are fine, but if you want to learn an ordinary differential equation, it is challenging to learn that because the library will just be too large. So usually what we try to do is better understand the dynamics first, try to find a coordinate transformation into a coordinate system where there are only a few relevant states that describe the dynamic, and then learn a differential equation in that new coordinate frame. Okay, these are the main, I don't know if these are the main challenges, but these are like the first challenges, and I think all of those challenges were already asked in questions in the first hour. So I think this is what we are going to discuss for the next part. And I have this short MATLAB tutorial that will probably crash, but you can just open the number 2 SINDy tutorial. So that's exactly the same. So let's just run it. Basically here, I prepared this MATLAB live script with a couple of sliders where we can play around with, okay, what happens if we reduce the sampling rate? What happens if we reduce the time span? So if we can only afford to collect 1 instead of 10 seconds, what happens if we add and then increase the noise level? So that would be basically the first quick thing we look at. So we saw this. So it's again the Lorentz system. So this is the SINDy model that we learned. So basically under the hood, what you can see here, just quickly go back, is that in MATLAB, we generate the data, and then we add noise, compute for the finite difference. We build the library, and then we solve our sparsify dynamics or our sparse regression. So exactly the same from tutorial 1. And now here, we can start playing around, for example, with the time steps. So this is how the model changes. So under the hood, SINDy is constantly solved. So you also see the speed of SINDy. This is quite nice. So if we increase the time step, we see that at one point we learn, oh, what is happening? We learn a couple of additional terms. Okay, but we also see that actually it's not too sensitive to the time step. Then second, if we start here with 10 seconds of data, what happens if we reduce the length of our data set? So first we see that, and then boom. At one point, if we only have, for example, 1 second of data, we will not be able to learn the Lorentz system dynamics anymore. But this is what SINDy would spit out. Okay? And now the main question, I think, with noise, so we already have a bit of noise here, but what happens if we increase the noise is this. So we start getting these spurious terms. And again, we still somehow see that, you know, there's like a -10 and a 10 here, something close to 28, -1, 1. So there's still a bit of the Lorentz system dynamics here, but we get lots of spurious terms because we use this not very noise robust approximation of the time derivative with the fourth order finite difference. Okay, so this is a tutorial that should give you a bit of an intuition of how sensitive the method is to noise, data length, and a sampling rate. But it's also a nice tutorial that shows how computationally efficient the SINDy method is. Because for each click, basically, on this slider under the hood, a new SINDy model is learned. Okay? So this is the first. Any questions here? Yes. Yeah.
Is this because of the noise that you're introducing into the system, or is this because the set of equations is chaotic, and then your finite difference derivative is introducing numerical noise if it's not very accurate? So if you picked parameters for the Lorentz system that weren't chaotic, would you still see this develop?
No, because you're absolutely right. So in the example before, there wasn't any noise. That's just the finite difference approximation. And you remember the equation that we learned is 9.999 instead of 10 because of the finite difference approximation. And because the system is chaotic, even a small difference in either system or initial condition will lead to divergence fairly quickly. So if we wouldn't have a chaotic system, it wouldn't diverge for no noise. And then what we see here is once we introduce noise, the model that we learn degrades even more, and they diverge even quicker. That's what we saw. I mean, okay, the example was second versus fourth order central difference. So there's already quite a big difference there, even for noise-free data. Right? Yeah, but that has nothing to do with the SINDy approach in a sense then. It's just the dynamics itself that is one of the main characteristics of them. So yeah, that's why it's, I think, also an interesting and challenging example here because it has all these characteristics. And it's related to lots of problems with care, like in fluids, for example. Okay, so let's go to the second. So model selection, exactly. So here we just sweep through the hyperparameter lambda. So again, we have one slider that changes our threshold. And then for each new threshold, we compute or we solve this sparse regression problem. Let's hide the code. And if our threshold log lambda, so that means that lambda is very large, so we threshold all coefficients, and we see that we just get x dot equals to 0. The other extreme, if our threshold is 0, we get the least square solution. So the solution is dense. We don't learn a sparse ODE. And now if we slowly start increasing our threshold, we see that something is happening. The first terms start disappearing slowly. The model is getting sparser and sparser. And it's too sparse. And it's gone. Okay? So let's do that once more. So this is the least square solution. We have this data set. And I think I added a bit too much noise, so we never really get the real Lorentz system here in this. I think change that back. Yeah, it's a bit much noise for the second example, so let's just move that back. Okay. There we go. Okay, so we start with our threshold being terribly small, so we get the least square solution. We increase the threshold, so coefficients that we learn that are below this threshold are set to 0, and then we see, there we go. This is the Lorentz system, okay? Linear in x dot, one quadratic term in y dot, and one quadratic term in z dot, okay? And if we increase the threshold even more, boom, they're also all gone. Then we only have, or we recover the trivial solution x dot equals 0. Okay? Just an example in terms of, okay, how does that threshold affect the model that we learn? And yeah, in the second part, I will discuss how we can find a more systematic way rather than just sliding from left to right to find the whatever best model means. Okay? And then the last part here, a bit of a challenge in terms of the selecting the library. So I chose a pendulum system that has basically, can I open this? Probably opened it before. Yeah. So second order ODE, x double dot is equal to something something times sine. That's the main part here. And we have a bit of damping, so that's our x dot. And I think that also answers maybe your second order ODE question already, because this is an example of one of those. Second order ODE, we have a pendulum basically that swings around. And what we see here in, we compute the derivatives, okay. This is the data set x and x dot that we can collect. And if we use our polynomial library, we get, in a sense, just like a Taylor expansion that fits the data. And we see, I don't know why it's a bit transparent, probably didn't solve properly. Let's run it again. And we see we can fit the data quite well. There's a bit of an offset here with this, let's say, non-sparse polynomial model. But what we can also do, if we have a bit of an understanding of the dynamics, is we say, okay, let's add a couple of sines and cosines to our library here. So this can be found in the pool data sign. In PySINDy, this is just adding a Fourier library. I think in the tutorial, in the Python tutorial, it's actually done properly in PySINDy directly. And then what we can see is that, oh, very nice, we can get, again, a sparse ordinary differential equation, second order ODE, that describes the dynamics of the pendulum. Okay, so I can recover that sine term. And if we compare, or if we run again on a test data set, I think I didn't even care about training and test data. It's, I think, the same initial condition. So I wasn't very careful here. But the point is that we can get a sparse ODE, and we can use it for forecasting, and it's accurate. Okay? But I think one point here is really, again, I don't just want to learn a model that can be used for forecasting. I want to better understand the data, and I want to learn a differential equation that can tell me something about that data. Because otherwise, we can just, we don't really have to care about the library too much and just learn a polynomial that does the job fairly well. But if we have some field or domain-specific knowledge and understanding, let's incorporate that into our library, and let's learn something that is meaningful, probably, and also generalizes better. Okay? So I think we have another 15 minutes. So I would suggest that we just all look at tutorial 1 and 2. You can also, if you have MATLAB, play around with the sliders, but the exact same tutorial with different types of libraries, noise levels, and the thresholding is also implemented in Python. So I would just recommend to use tutorial 1 and 2. And if you have any questions, just discuss. Lloyd is also a SINDy expert. So very good. Yes. Mm-hmm. Mm-hmm. Yeah. So there is quite a lot. No, no, because, I mean, it depends. If your noise changes, it depends on the time scale of the change of your noise. Because if you're interested in a whatever snapshot around X amount of time, vanilla SINDy would work if you have the appropriate way to deal with noise, let's say. But then what you could also do is to think about learning a stochastic differential equation, where you learn some drift and diffusion terms that can describe how noise behaves, how it changes maybe over time. So there's quite a bit of work around that. And then the latest work that I am recently working on is thinking about some guarantees of coverage of your prediction using conformal prediction. So that is something that might also fit. Yes. It is basically a way to find guarantees on the coverage of a forecast while minimizing the width of an interval, in a nutshell. And the idea with using SINDy, I mean, it's basically agnostic to the model that you're using. You have whatever forecasting model, and you want to find a way to describe how certain you are about whatever these forecasts. And so I put something on arXiv that discusses the idea, but it's still a bit wobbly. So SINDy and conformal prediction.